All right, welcome everyone to Spring 2025 Intro to Space Navigation Lecture 15. Go. There it is. Lecture 15 is going to be lecture long unit on inertial navigation. So we talked about, just as a reminder, we did our orbital mechanics lectures, then we did estimation theory, and then we did just 2 short lectures on triangulation and trilateration. And roughly speaking, each of these units is a homework assignment. So homework 1 was orbital mechanics, orbit propagation, and IOD. Homework 2 is estimation theory, and that's due tomorrow. Homework 3, triangulation and trilateration. You now have everything that you need to do well on homework 3. That'll be due in 2 weeks, but I think there's a chance that we might move the deadline on that. Today only, we're going to talk about inertial nav, which is a neat topic which is worth your awareness, but it doesn't really fit neatly into a homework assignment. So I'm going to say something that is probably dumb for a teacher to say, which is that today's lecture will not appear on any homework assignment. And I realize that causes then a tendency to kind of zone out. So it's up to you. Today is meant to be just kind of a for-year awareness. We're going to talk about inertial nav, but you can kind of relax a little bit. And then when we get back, we're going to talk about cameras and kind of camera-based navigation. We'll talk about star trackers. We have a whole star tracker unit. That one is going to have a homework assignment, and it's going to be pretty gnarly. So enjoy homework 3 and then no homework on inertial nav. Star trackers is first thing after spring break. So, yep. And let's out inertial navigation. So this is really the beginning, and actually I want to go back to our diagram here. This is really the beginning on the spacecraft side. So you'll notice that from the spacecraft, we have kind of 4 things emanating from it. So there's inertial nav, there's the sequential estimation that you can do on board, which is Kalman filtering. And then there's 2 different types of image-based navigation that we'll talk about doing. But all of these are things that the spacecraft does. So by contrast, triangulation and trilateration is something that involves the Earth, right? So either you're taking Earth measurements of the spacecraft or spacecraft measurements of somebody on the Earth, but it's kind of an Earth to space, a space to ground, ground to space, that sort of thing. Now we're beginning to talk about autonomous navigation, so entirely on board the spacecraft. So as a reminder, from our definition from the very first day, navigation is determining a vehicle's state. And by state, we generally mean position, velocity, or attitude from available measurements. Okay, so what types of measurements do we have? So what kind of measurements? Well, one way to separate these is external measurements and internal measurements. So if you're using the human body as a kind of a metaphor, then as you're drifting through space trying to figure out where you are, you can look at things, you can receive signals. I guess maybe that would kind of be analogous to hearing, not exactly. Still, you're communicating with light when you do triangulation and trilateration. Your camera is very closely analogous to your eyes. Kalman filter, I guess, would be like your brain. That's kind of the flight computer. Inertial nav is a bit different. So we're not taking external measurements, we're taking internal measurements. So external measurements is generally light. And so the kind of analogy here would be like human eyes. But then internal measurements would be something like the human vestibular system. And so I don't know why this is the first thing that pops into my head, but I distinctly remember when I was really young, my parents took me to a shopping mall and we bought a toy that I really desperately wanted. I must have been like 7 years old. And it was I don't even really remember what the toy was. I just remember being really excited. And it was the sort of toy that you couldn't really play with in the car. You had to go home and like unbox it to enjoy it properly. And I was so giddy with excitement to get home from the mall and open this toy. And we hit a really bad traffic jam on the way back from the mall. And it was just torture for me. I was like, come on, like I got this thing, it's in my hands. I just want to open the box and have fun. And I was losing my mind. And I remember that one of the tricks I tried to play, the same way that if your video isn't loading on YouTube, you can kind of pretend that you're not interested and like psychologically you think that's going to make a difference. I pretended that I wasn't interested in getting home, and I even closed my eyes and pretended to go to sleep to kind of convince the powers that be that I was not interested in actually opening this toy. And I thought, oh, this is perfect. I can just, open my eyes and maybe we'll be halfway home if I keep them closed for 5 minutes. I mean, you never know. And I promise I have a point to this story. I realize we're kind of we're weaving around here. But as we were sitting in this stationary car, I opened my eyes and saw that we hadn't moved, which was, again, torturous to me. Closed them again for 2 minutes, and I realized I didn't need to open my eyes. I could feel the car, right? Like even with your back and with your butt touching the seat, you're getting nerve ending signals. You can tell whether or not a car is in motion. You can tell whether or not you're turning. You kind of feel that sway out to the side, that sort of thing. Your body has ways of determining whether or not you're moving that aren't visual. And these are largely based on your vestibular system or just the feeling of pressure on your body, that sort of thing. So all this to say, I promise there's a point to this. If you sat in a car with your eyes closed, you could still tell whether it was moving. Your built-in human body sensors can detect acceleration as well as rotation. So you might say, why can't we do this on an aircraft or a spacecraft or a submarine? Anywhere that you might not always be able to get good nav measurements? And the answer is we do. We do this all the time, and that is inertial navigation. So an inertial measurement unit, or IMU, is a sensor suite that takes inertial measurements. That can be used for navigation. Navigation done using these measurements is called inertial navigation. And this is similar to something that you might have heard of. It's called dead reckoning. We'll explain that in a second. An IMU consists of accelerometers and gyroscopes packaged together. Gyroscopes measure rotation, and accelerometers measure what I'm going to call felt acceleration. Be careful about that. And so we'll talk about this a little bit more explicitly later, but you might say, look, if I have a sensor that can measure acceleration, can't I just take two integrals of that to get my position and just keep a running total of my position forever based on the acceleration? And then, yeah, there'll be some noise, but in general, I'll have a pretty good sense of where I am just based on acceleration. And the answer is absolutely yes, and we do that all the time on aircraft and submarines, but that won't work in space. And that is a major, like if you're talking to people who do missile guidance and they talk about just integrating your accelerometer, and you try to explain, it's like, that's great for missiles. That doesn't work like on the way to the moon. That can be a tricky point to get across. And I've been a part of conversations where teams that are used to this sort of thing working are shocked when it doesn't work in space. So we'll talk about that in a little bit. First, got a story for you. I just think this is fun. So in February 1953, a B-29 Superfortress, it's an airplane, took off from Bedford, Massachusetts, and flew to LAX, Los Angeles International Airport. It flew the entire, we'll call it 3,000-mile journey. With no input, we'll say with no human input. And was less than 10 miles from the runway when pilots took over. So basically, the plane flew itself from Massachusetts to Los Angeles. It flew on autopilot. Right? And you might say, big deal, planes do this all the time. And I'm saying, huge deal. This was the first time this happened. Up until this point, a human was at the controls the entire time. This was, we took off, we got the thing nice and level, we took our hands off the controls, and we just let the plane fly itself. Nowadays, planes can fly themselves routinely. I mean, this sort of thing is commonplace, but it had to happen for the first time at some point, and that was February 1953. Here's the cool thing. Control was given to a flight computer equipped with an early IMU the size of a washing machine. Which was developed at the MIT Instrumentation Laboratory And so, yes, the RPI instrumentation laboratory, where we all pretend to work when we're doing our homework assignments, is a tongue-in-cheek reference to the actual MIT instrumentation lab, which did some of the very early navigation work, like really early stuff. Actually, MIT instrumentation lab is really cool. We could go on a whole tangent about them. They did some neat stuff. On board was Dr. Charles Stark Draper. Yes, that Draper. So Charles Stark Draper was the head of the laboratory. And so those of you might be familiar, there's a company which is one of the foremost navigation companies, that creates the algorithms, the flight software, does the development work. That is called Draper. I have a bunch of good friends that work at Draper. I myself interned at Draper many moons ago. That Draper was named after this guy, Charles Stark Draper, and it was originally the MIT Instrumentation Laboratory. So it kind of split off from the school, became its own company, that sort of thing. Charles Stark Draper was on his way, I think this is so cool, to a conference, to an academic conference, to discuss if inertial navigation would ever be feasible in practice. I just think that's so delicious. So he showed up to a conference about whether or not inertial nav would ever really make sense on an airplane. And he flew there on an airplane that was doing a live demonstration of inertial nav. I mean, this is the sort of thing that Tony Stark from Iron Man would do. This is the type of engineering showmanship that you just don't hear about anymore. So this technology and these people, Draper and friends, would prove essential on the Apollo missions. So the MIT Instrumentation Lab original claim to fame was they made the Apollo guidance computer and then wrote the software for it, that sort of thing. So moving on from that, we're not talking about Draper today. We're talking mostly about the IMUs. This was called a platform IMU. So platform IMUs, like the ones from Apollo, relied on a gimbaled platform. Oh, sorry. Also don't know why I capitalized the G. They relied on a gimbaled platform to isolate the sensors from the rotation of the vehicle. Another option is called strap-down IMUs, which is more common today. So back in the day, you needed an actual platform, as a stable platform, which would not move as the spacecraft moved around it. It would obviously they would translate together, but it would not rotate with the rest of the vehicle. It would be fixed in inertial space, and then you could measure your orientation with respect to that object, that sort of thing. Strap-down IMUs, you can just, as the name implies, just bolt them to your spacecraft, and they work without an inertially stabilized platform. So this is more modern. Rotate with the vehicle. So a few things to consider. Angular velocity is constant throughout a rigid body. Angular acceleration is not. So this drives the placement of strap-down IMUs. So you have to actually think about, like, where do I want to mount this on the vehicle, given that you're going to see more acceleration further away from the center of the vehicle and then less towards the center, that sort of thing. Okay, so we talked about an IMU is accelerometers and gyroscopes. Let's linger on gyroscopes for a little bit. So gyros, it's the kind of common abbreviation for gyroscopes, measure the inertial rotation of the sensor frame. So there's a few different types. One is mechanical gyros. Think Apollo era. Consists of an inertially stabilized platform. So again, platform IMUs. Connected to the spacecraft by a gimbal. This is the gimbal from gimbal lock fame, right? So the idea would be, do I have any? Hang on, stand by. I don't have any pictures in my notes for today, which is a real loss, although my art skills are kind of dubious at best. But to understand this gyro system, imagine that you've got some base with some ring. Unfortunately, I kind of need to draw these rings today because we're going to have a perspective issue if we don't. So you've got some base, here's a ring, and this thing is allowed to rotate. Like yay. There we go. But then it also has some other ring, which I'm going to try to draw at an oblique angle, inside the original ring, which is allowed to rotate like yay. And then that has another ring inside the first two, which is allowed to rotate like yay. So you end up with these three axes of rotation that allow something in the middle of all of this, kind of the innermost part of this kind of Russian nesting doll, can have whatever orientation you want, asterisk, right? You can't just spin this thing around willy-nilly and never have a problem. If you align your first and your third axes, for example, then you actually have the thing locked. And that's the gimbal lock problem we talked about before. But the idea is this innermost platform should stay completely fixed with respect to inertial space. And as your spacecraft moves, it moves around this thing, and this thing is locked in place, inertially speaking. So that's why it's inertial navigation. And then you can read off the angles from your gimbal, and that would give you your roll, pitch, and yaw. That's basically the idea. But then there's some issues that go along with that. Gimbal lock being one of those issues. Now, generally, we don't do this anymore. More modern gyros are optical gyros, like the ring laser gyro. Sounds really cool. And fiber optics gyro. are used for high performance spacecraft navigation today? So Orion, for example, would use a ring laser gyro. There's also Coriolis vibratory gyros. Are smaller, cheaper, less accurate, perfect for smartphones. So your phone has a Coriolis vibratory gyro in there. And the idea then is you have a oscillating, kind of a spinning, or I believe it's a linear oscillating kind of micro pendulum. And then there's going to be a tendency to resist changes in orientation, because this thing, if it's spinning, it wants to kind of stay oscillating in its same plane of motion. And then if you attach just a tiny little force meter to that, you can detect the amount that you must be rotating. And I mean, these things are absolutely tiny. They fit in your phone. They're nowhere near as good as the stuff that we have on spacecraft, as you might expect. But there are plenty, for example, when you turn your phone on its side, it knows that it's on its side. This is what that is, essentially. That's a Coriolis vibratory gyro. Also, you'll need a CVG for something like virtual reality. Like your VR headset knows when you look around the room, it can do some math and go, oh, they're looking over there now. Okay, load up a different scene. So this is also something that's done that way as well. Oh, you know what? I got ahead of myself. I just said is the notes for the next section. So stay with me. Optical gyros operate on the Sagnac effect. A consequence of general relativity. A beam of light is split, travels opposite directions, around a closed path. Okay. If that path, if the path is rotating, light has to travel longer in one direction. So a sensor measures the phase difference between beams of light. So if that makes sense, you have a ring, you shine light around that ring forwards and backwards, and ordinarily it should take the same amount of time for the light that took the right path to get back to some sensor as it would take the beam on the left path to come back to that sensor, right? So it's the path is of the same size, that sort of thing. But then if you were to rotate in that plane, the light would have a longer track along one direction than the other. And you'd actually be able to measure this as a phase difference between the light that arrives at the sensor. And this would give us the rotation along one axis. So this would give you a component of your rotation. You would need 3 of these optical gyros to get the full 3D rotation, if that makes sense. And next is Coriolis vibratory gyros, or CVGs. Measure the force required to rotate a vibrating object. So vibrating objects tend to want to vibrate in the same plane. Rotating a vibrating object produces a detectable Coriolis acceleration. That's where the Coriolis part. So you've got something that's vibrating. As you rotate it, there's a Coriolis acceleration. So you have a Coriolis vibratory gyro. Okay. So this is great. Let's talk in terms of nav. I mean, we haven't talked about any math yet. There will be a small amount of math in this lecture. When the time comes to come up with a mathematical model that describes the relationship between the actual rotation of the vehicle and the sensed rotation of the vehicle, we need to start thinking about error sources. So we'll focus on strap down IMUs for now. So be thinking about, okay, you've got one of these devices. What are all of the things that would confound you being able to measure the true rotation of the vehicle? So I can think of 5. The first is scale factor error. And that would be conversion from voltage or digital numbers to engineering units. The next is misalignment error. Which is just to say that you have not mounted the sensor the way that you think you've mounted the sensor. So the attitude of sensor frame with respect to the vehicle frame is slightly off. Another is non-orthogonality error. Remember how I said you need one of those ring laser gyros to measure the X rotation, another to measure the Y rotation, another to measure the Z rotation? What are the odds that when you installed these on your spacecraft, you installed those sensors perfectly orthogonal to one another? And you might say, well, why does that matter? Can't we just get it close? It's like, no, you kind of need to get it perfect. And you won't get it perfect, and that's fine, but you need to account for that error. We cannot just assume that it's perfect. So your gyros, 3 of them, were not mounted perfectly orthogonally. Another is sensor bias. And that would just be an offset in measured body rate. So if for some reason you are measuring a rotation when your vehicle is not rotating, and then, let's say you're off by a tiny fraction of a degree per second, that's going to persist, right? You're always going to be off by this certain bias. That bias might not be constant, than the aliens model. And then the last one is readout error, which is just noise on the gyro output. All right, we're getting dangerously close to some math. So this is the way we're going to think about our gyro error. Okay. Beginning with only readout and bias. So our simplest error model is just going to assume there's no scale factor error, there's no misalignment error, there's no non-orthogonality error. This is, you can get this to fly. It would be nice if we were a little bit more thorough, but this is a good starter point. So we're going to say that omega is going to be our measured body rate. So you could think of omega x, omega y, and omega z as our rotation in the 3 body directions. This is the vector omega. So omega plus a bias vector plus a noise vector, that's nu. All of that is some noisy omega, if that makes sense. So this would be measured rate. This would be the true rate. This is bias. This is noise. And we'll also say that the noise has a measurement covariance of sigma nu squared I 3/3. So we're assuming that each of our 3 gyros are, in this case, they have the same noise on each of them. Now you could go through and say there's different noise on X, Y, and Z. This is our kind of simplest error model. So this is the Fahrenkopf gyro model. The simplest used in aerospace applications. We do not treat bias as constant. So the bias, the amount that your sensor is just a little bit wrong all the time, is better treated as a random walk, or, to be fancy, a first-order Gauss-Markov process. Which is similar to a random walk. So this is how we would model out. We're going to say that it's got some differential equation. It's got B dot is -1 over tau B plus eta, where tau is correlation time and eta is white noise. So essentially, this is the random walk term. And then this is a tendency to return to normal. And to see this, let's just consider what the equation would look like if we were to drop terms. if you have a bias where the derivative of your bias is a random number, then you're going to have a bias that naturally wanders around. And if it's a 3x1 bias, you can treat it as some point in three-dimensional space, which just naturally wants to kind of wander around. The issue is that a bias that is that simple, it can wander off, right? So imagine you've got, this is your three-dimensional space. Let's say you start with some point here, and then it just kind of wanders all over the place. There's no particular force that would make it want to go back to its point of origin. So you could have your bias wander off. We try not to do that, right? Because in all likelihood, whatever your bias is, it might change a little bit, but it's not going to change drastically. So random walk, not good enough. If b dot is some constant times negative b, then that is just simply a point in space which wants to return to the origin. Right? If the derivative of if your velocity is opposite your position, you think of it that way, then you're always going to want to go back to the center. This is why if you're taking a controls class and you see that x dot is negative x, then you know that this is going to be a stable system. You know that things are going to want to tend to go back to the center. Whereas if x dot was positive x, or some scale factor of positive x, then it's going to tend to blow up. It's going to say, well, whatever our velocity is, it's in the same direction as our position. That's unstable. So the combination of these two things is a random walk with a general tendency to meander back to the center, but not necessarily. And you can adjust these parameters. So adjusting tau will make its kind of homing signal stronger or weaker, and then adjusting the noise will make its kind of jumpiness stronger or weaker, if that makes sense. So that is a first order Gauss-Markov process. That's the way we're going to treat bias when we put this into a Kalman filter, which is obviously not this lecture. Okay, what about misalignment error? So we model this as a small rotation. So whatever we thought the spacecraft to sensor transformation matrix was, we were wrong. So we need to account for that. So now we're going to say omega with noise is some delta t omega plus b plus nu. Now in this case, bias and noise are unaffected by the rotation. Because they have to do with sensor electronics. All right, now this dt, that is our attitude transformation matrix. It's going to be a small angle, right? If the matrix delta t corresponds to an angle vector, small angle vector, we'll call that delta phi. So we're back to angle vectors from lecture whenever that was. Then we can say that delta t is the identity matrix minus delta phi cross product matrix. Or for the sake of derivation, we could say that this is I plus. So we're just defining E such that E is the negative cross product matrix of this small angle vector. So our original equation becomes that our noisy measurement is identity matrix plus E, which is something that we would need to find out, omega plus B plus nu. All right, let's go back. We've now talked about sensor bias. We've talked about the pure noise, the readout error. We've talked about non-orthogonality, or sorry, we've talked about misalignment. Next is non-orthogonality. So we account for non-orthogonality with the transformation delta G, which is not orthonormal. So this is not a direction cosine matrix because a direction cosine matrix is going to have a determinant of 1. It's going to have a norm of 1. It's going to be something that only rotates and does not scale, and it preserves orthogonality, right? We don't want that. We actually want something that causes this kind of shear, if you can imagine, that now all of a sudden your new x, y, and z unit vectors are not orthogonal to one another. So a pure direction cosine matrix won't accomplish that. So what we're going to say is that delta G can be approximated as the identity matrix plus gamma, where gamma is this lower diagonal matrix, gamma 1, gamma 2, gamma 3. Oops, sorry about that. And then all zeros otherwise. And these are calibrated values. So we would either know these or determine these. Okay. And that means that now we have, let's see, we have non-orthogonality affecting our small angle error, affecting the true value, and we have a bias, and we have noise. All right. Finally, we account for scale factor error. So we're assuming there's going to be some scaling problem. By scaling the output by I plus S, identity matrix plus S, where S is a matrix which is diagonal. It's got an X scale factor, a Y scale factor, and a Z scale factor. Okay. So that brings our entire model. So our full sensor model is I plus S, and this actually would apply to everything. So this is a scale factor error on the measurement, which includes the bias and the noise. And then we would go through and say, okay, I plus gamma, I plus E, the truth, plus B, plus our new term. And if we assume all errors are small, which I hope so, and keep only first order terms, that is to say, if we go to the effort of multiplying this all out, then S times gamma is small times small, which is really small. Gamma times E is small times small, which is really small. Then we get a simplified model. Which is this. I plus S plus gamma plus E, the truth, plus bias, plus noise. Where the error terms, see, how many things have we introduced here? Well, there's SX, SY, SZ. There's gamma 1, gamma 2, gamma 3. And then there is delta phi, which is itself a 3x1. So that's going to be 9 terms total in our error model, are calibrated before flight. And the bias is estimated as another state. So remember, we learned the trick about if we have some parameters which are kind of annoying, which for whatever reason we can't afford not to know, then we treat that as part of the state. So on a real navigation filter, it's got position, velocity, attitude. It's got things that you would expect to see, but then you'll also be tracking loads and loads of these little bias and error terms here and there, which kind of have to come along for the ride or else the whole filter won't work. All right. So let's see. I think ordinarily we try to break at the top of the hour, but I've got half a page of notes left. I'm just going to push through. I want to talk about accelerometers, and then we'll break. Break as in like we'll be done. So accelerometers, I mentioned this before, measure felt acceleration. This is when the vehicle is pushed. So accelerometers only provide useful data when an external force acts on the spacecraft. Gravity is not an external force. It affects sensor and spacecraft together. So this is key. You cannot directly measure the gravitational field using an accelerometer if you are in free fall. Right? If you have an accelerometer and you set it on a desk, then it will go, okay, yep, 9.81, got it. But if you chuck it up in the air, then it will actually feel less and less acceleration. There will be one moment at the top of the arc where it feels no acceleration. The same way, like when you're jumping on a trampoline, you have a split second of complete weightlessness, and then you come back down again, and then it would feel itself once more. In free fall in outer space, when astronauts are kind of orbiting the spacecraft, for example, in the ISS, that kind of pure moment of weightlessness at the top of the trampoline never stops. Right? So it isn't that gravity isn't acting on them; it's that gravity is acting on them, and gravity is acting on the space station, and the relative motion between them you can't really detect. So you could think of it like when you're sitting in a chair, you know that you're sitting in a chair, not because you feel gravity, but because you feel the ground pushing up on your feet and on your butt and on your back. But you wouldn't feel that in space because there's nothing pushing you along. So there's no felt acceleration. That's the key difference. For a submarine, yes, this works. For an airplane, yes, this works. When you're in space and you're floating, your accelerometer is floating too, which means it's just garbage coming out of it. Until you fire on your engines. All of a sudden, you have some felt acceleration. A burn or orbital maneuver . is an external force. So accelerometers really only matter. Actually, I have this as my next note here. Thus, accelerometers are useful in space whenever the crew needs to buckle their seatbelts. But during coast, no data. Another key thing, accelerometers are not mounted at the center of mass of the spacecraft, because that would be impossible, or at least impractical. Therefore, they measure acceleration due to rotation, as well as translation. So we'll need to take that into account. Just because your accelerometers are feeling something doesn't mean you're actually translating or firing on your thrusters. Doesn't mean you have a linear acceleration. You could have angular acceleration that it would measure, and it would pick that up. So fundamentally, accelerometers work by measuring force required to accelerate a proof mass. So this is Newton's second law, essentially. Total acceleration on the vehicle is, so you've got the actual spacecraft acceleration, which is the total acceleration, is equal to the acceleration caused by gravity and the acceleration as measured by the IMU. And we use a mathematical model to estimate acceleration due to gravity. So we've got pretty high fidelity mathematical models of the Earth and the Moon, that sort of thing. So we just say, okay, based on our current position and based on what time it is, based on the location and the orientation of the body, this is what our gravity would be. The basic error sources are the same as a gyroscope. So we use similar error model. So the acceleration, noisy acceleration that comes from an IMU is equal to I plus S plus gamma plus E. These are all for the IMU, right? So you would need a different one for the accelerometer. And then you've got the truth plus a bias plus noise. And that's about it. That's all I have to say about IMUs. They don't really fit neatly into any of our homework assignments, so we're not going to have an IMU homework assignment. But as much as I don't like to admit it, as a proud spacecraft vision or image-based navigator, I like to think that cameras are the king of spacecraft navigation, but they're really not. IMUs are the king of spacecraft navigation, especially of attitude. So if you're measuring your orientation of your spacecraft, it's the IMU that's doing the heavy lifting. The same way that your inner ears tell you which way is up and which way is down, even when you're underwater. Right? But then you can open your eyes to make sure that you're correct and you didn't just get disoriented. And similarly, when IMUs start to drift, we can take an optical measurement, say with the star tracker, and allow it to realign the IMU. But yeah, IMUs really are king, even though my personal preference is for cameras. Anyway, that's pretty much all I have to say about this topic. Do we have any inertial nav questions? Otherwise, we can stop the recording and kind of transition to office hours for homework 2.
So just general question. I'm assuming when you're dealing with this kind of data, if you're not dealing with spacecraft, most of the time you're just using the IMU and the accelerometer and are happy moving on. Or is there one between the two of them that you know is preferred?
Oh, I mean, outside of spacecraft navigation, you'll still need to take external measurements. So in general, I guess I should have leaned on this a little bit more heavily. When you're only doing inertial navigation, that's called dead reckoning. So it's like, okay, well, I knew where I was at this time, and these are all of the motions that I've sensed in the intervening time. And so by just integrating that, I know that I should be about here. Or you could even say in space, you could be like, well, here's what my state was. Here's the gravity that I was subjected to. I'm pretty sure I should be at this future point. But at some point, you need to open your eyes and take another measurement to make sure that you're not just going crazy. And that would be an external measurement, which we'll talk about that in our Kalman filters unit. But even for aircraft and submarines, you would use something like GPS or some other nav technique to kind of tell you where you are. But your dead reckoning is really like that's going to give you a nav fix at 10 hertz, 100 hertz, whereas you might only be able to get a good, GPS signal, more sparsely, that sort of thing. Does that answer the question or not exactly?
That answers most of it. I think I was more curious, like, when you're doing internal navigation, like assuming you still have that external input, is there typically some kind of preference over using accelerometers versus gyros, or is it like most of the time everything they're cheap, they equip them with everything and move on?
Oh yeah, they do equip. These things are cheap, so you just equip them with everything and move on. So you wouldn't do accelerometers or gyros; they typically come together.
That makes sense. Thank you.
Yep. And there's another instrument which I learned about fairly recently, but this was really king, and I think is still very useful for low Earth orbit. But if you have a accelerometer set and a gyroscope set and a GPS receiver, you're basically done navigating, and that's called a SIGI. So they had SIGIs on the space shuttle, that sort of thing, and that would be how they would get there. So you get your position and your orientation and all of your accelerometer data. And after that, you're just laughing. So once you have nav in a box with your SIGI, SIGIs won't work quite as well when you're going out to the moon, that sort of thing. But yeah, navigation is. I want to hesitate to say that it's solved in low Earth orbit, but a lot of the really exciting navigation problems are out in the middle of nowhere, which makes sense, right? As we kind of continue to explore, we solve navigation problems as we go. So all the coolest stuff's going to be on the frontier. Anyway, um, cool. I think that's a good spot to stop. I'll end the recording, and we have plenty